Okay, we'll come back for this lecture, and the today lecture is going to be run by Francesco Lovergine. You met him during the introduction presentation. Francesco is a great developer in Linux environment from many years, much more than me. And actually, he was introduced in the Linux environment. Say you have to start learning Linux, and this is where I am now. Okay. So it's a good resource for me and for everybody to ping him for question and so on. Today, we're adding this session under the Python environment, where we are going to deal with mainly entering the GeoPython, the use of Python for geographical operation. There are going to be another session in the GeoPython environment, run it also from PK tools, the Peter developed, other way around, Peter, the developer of PK tools. And so today, Francesco will focus on Rasterio. Okay, it's a package that was coming up, I think, 10 years ago, maybe even less. Well, it's quite recently.
Yes, I think 2009, something like that.
Yeah, something like this. And he will see he will start to use the Rasterio package. In these regards, the data set that is going to use it, they are going to be the data set that we are going to use it for the machine learning application. So just to spending really few words about this data set. This data set that we are going to use it are the JDI data set. Is a laser scanning satellite that has been launching like 4 years ago and is continuing launching impulse to the Earth, and is very useful to get the height of the digital elevation model and also of the surface and terrain model in particular. So these are very useful for doing especially derive tree height of or building height and so on. There are different beam and laser in the spectrum of the impulse, and we will go deep in the implementation and what they are when they what they are for doing the tree height estimation. For now, I just want to say that there will be points with a lot long information, and for each point we will have the tree height. Okay, so and of course the tree height will be used here. There's a picture is not coming, but maybe it's the loading. And the tree height, as you know, is influenced by several land cover, several environmental characteristics like humidity, precipitation, temperature, species, quality of soil, soil characteristic, and so on. So we are going to do it a regression analysis in the machine learning environment in order to retrieve the tree height. Okay. Anyway, we will go deep in the data set for the instrument implementation and so on. For now, just consider that Francesco is going to use this data set in Rasterio to see how use it Rasterio. Okay, with this small introduction about the data set, we can jump again to the, I can give the words directly to, and under Python here, you will see, please refresh it. Sometimes it's not coming out. It's depending from the cache. Now, yes, yeah. So under Python, you can follow by the web page, or you can follow by the typical rsync and git pull. So Francesco is going to review this part over here. Okay, to you the words, Francesco. Let's stop sharing.
Okay, thanks. Let me share. Okay.
Okay, yeah, we can see.
So I share my session in a virtual machine. You are basically able to the virtual machine terminal session. This is the page you are you can see on the web page too. So in order to follow me in the interactive session, you can simply do what is written here, so that you can. I think you have already synchronized your own directory with the Git archive, and you can run the Jupyter notebook, this notebook page, in order to follow me. So this is the very first meet with Python and Python packages and libraries. Python is currently the most prominent language used in data science in all domains, in all science domains. It became so in the last, I think, 10 years, maybe 15 years. The language is quite old now because it was born in the 90s. The power of Python is due to the possibility to use a lot of different packages that are not Python native. So they are based on external libraries. One of those libraries you already know is GDAL. A nice joke is about how you pronounce the GDAL library. That's because it changes during the time. If you think that the GDAL was born in 90s too, and the main author of GDAL is Frank Formadam, that was for a period in Google at the time when he founded the project, the GDAL project. He worked for PCI Geomatics and started with a library that should be good for all. Good for all means GDAL. So he pronounced that library as GDAL for that reason. Now he changed his mind about that. So GDAL is the official name of the library. Basically, the GDAL was born as a library to simply access different formats used in the geospatial environment. But in the course of time, the last 20 years or more, it has become something a bit different, because it now is usable to perform a lot of different operations on geospatial information, on geospatial data, both raster and vector. You already use that in some way by using the GDAL tools, which are the binaries that you can use to perform a lot of different operations on the data. So I'm now presenting this raster.io or raster.io package, which is something like the Python version of GDAL. It is not exactly the GDAL version of in Python, because GDAL has its own library in Python that is called the GDAL binding in Python, which is much basic in some way. The reason why a lot different people, different teams starting to use to write something different in respect with the GDAL binding is that the GDAL binding, so the proper GDAL library in Python, is not too Pythonic. It's a bit rough because it's based on the original library. This is written in C and C++. So it's quite articulated in user. You need to go quite at low level if you would like to use the GDAL binding. So that's a reason to have a package. In this case, raster.io. That is so that the goal is to simplify the use of the GDAL library. Indeed, there are a pair of different libraries that you can use in Pythonic way. One is raster.io, the other one is Fiona. Both them can be used to access when the raster for the raster files, of course, and Fionas is usable for vector data. I think you could already access this create directory in your own area. This is available from a Google Drive repository. So I think in the meantime you already downloaded those data. The dataset is quite heavy, so you should try to download it if you're not already done in another moment, because it requires quite a lot of time. Anyway, you should also already installed Rasterio by pip executable, so using pip3 install Rasterio. And the way to proper use Rasterio is simply import the library in a Python interpreter. You now are in the notebook per default you are using the Python 3 kernel. So you can write simply Python code and see the result. The 1.3.2 version is essentially the current one. You can know the Rasterio version, the current version, by simply printing the version, the dash version dash variable in a Rasterio package, and see if you are working on the current version. The development version is, I think, is a 1.4. So you should use for sure the 1.3, which is the current stable one. One of the first things you have to do is, of course, opening your dataset. In this case, I'm using one of the file in create geodata raster directory. This is an elevation, so it is an elevation file, so it's them. When you open by Rasterio, you have to specify, this is the default, the mode in read-only. The read-only mode is the default way to open an existing dataset. You could also use other way to open, other modes to open the dataset. So you could be interested in writing a new dataset, or also open in read and write mode to modify it. Of course, the open call has a lot of different options that can be used to open a raster file. Just for information, of course, a raster file could be multi-bands and also multi-resolution. And generally speaking, not necessarily it is a single file, a single matrix, to say better. You could open a raster file which could contain both raster data and other variables. It depends definitely on the format of the file. There are some formats that are not GeoTIFF, which are used as a sort of containers. So a lot of different raster files could contain, for instance, netcdf or HDF5, could contain not only a single or a group of metrics, but also scalar variables and vectors, along with other multiple matrices and multiple bands of different data type. And so could be truly a complex data set, including a lot of different information. So when you open by Rasterio, you access generally all those information, but this is typically defined using a specific UL definition here. So for the name, for instance, when you open netcdf5, you could open one matrix of the CDF file by simply specifying this dataset here. I don't know if Giuseppe already shown this in using, for instance, GDAL info, but I think so. But essentially, so you should specify the correct URL to access the data you're interested in when using the open code. So when opening, you could also specify the data type among all valid data types, integer, floating point, and so on. You could also override the no data definition by specifying it at in the call. You can specify the spatial reference information and also the size of the data set, the size of the image or the images, the geotransformation, the geotransform matrix to use, the number of bands to consider within the data set, and also the driver. Of course, some of those parameters can be useful for both writing or reading data set. So if some of this information are available in the already an existing data set, they are used for overriding what is present here. Yeah. But in general, most of those parameters are used for writing and so creating a new data set. Here you can find in this documentation, you can find a complete. Let me open this one. Okay, so this is the complete reference to specify this information here. Most of them are quite descriptive in the definition. Some of those information could be optional. For instance, GDAL allow you to specify, for instance, information about driver options. So you could be interested in reading by changing, for instance, the caching, and so to get a lot more efficiency in accessing the data file. Some of those specifications are even very specific to the URL you used here. For instance, you could use also for a URL that is specifying a zip file, and you are interested in the content of the zip file, or you could be specify an AWS S3 storage, and so you are pointing to a remote storage. All those URL are legal in Rasterio, and you could use them to open this kind of data set in a single code. Let's see for a few. So consider to have open this data set. The data set is an object, and you can specify in this case the main method you will use will be dataset reader. This is a function specified. This dataset retain its name. In this case, 3H data raster elevation TIFF. Its mode, this is specified in terms with a single character. You can also specify during the script you are writing, you can check if the dataset is in any moment is still open or you closed it. So this Boolean variable will return false in this case because we just opened that data set. You can also find if the number of bands here included. This is a DAM, so there's only one matrix here. This would be a number greater in the case of, for instance, a Landsat 5 or any other kind of multi-band data. You can find directly, yeah.
Francesco, when you when you close the data set, is writing back to the disk, or it's just a closing?
No, here I specified the R mode, so it is in read only. When you close, it is closed, but you can alter this data set because it is open in read-only mode. You have to specify a different mode in order to change this this mode of operational mode.
In that case, when you close, it's going to write to
when
the
you
disk.
close, it is saved. Yes, if you use the as we will see a write method instead of the read only, the read method, you can also modify the data set, and when you close, all information will be saved on disk.
Perfect, thanks.
Of course, if this is a remote session, so if you are accessing a remote session, when you open in write mode, it depends on the driver. You know that when you specify a different driver that is not a GeoTIFF driver, but for instance a remote access, for instance S3, you will have to ensure that you have the right permissions to write if you change something in the raster dataset, and all this depends definitely on the driver specifier, on the driver used. So dataset bounds is again a method that allow to know what are the geographical coordinates of the corners of the image. In this case, this is the longitude and latitude specified in WGS84. That's quite evident by the numbers. You can access the geotransform. In this case, you see this is an affine geotransform. This is absolutely similar to the information that are stored in by GDOL as a geotransform. Rasterio is able to specify at least 3 different methods of storing a geotransform for your data. The most common is the affine, but you could also define a georeferencing by using ground control points, or even rational polynomial coefficients. Both them could be used. It depends on the kind of data set. For instance, if you use a non-auto-rectified satellite image, probably the vendor will provide you with RPC coefficients in order to integrate those coefficients with the altitude and get an auto-rectification operation directly by using this kind of geotransformation. I don't know if Giuseppe clarified this this detail about the reason why the minus in resolution is present in the geotransform. Someone asked for that. I know. Anyway,
yeah,
this
it was Martin question, I think.
Yeah, this is due to the north-up orientation of the image of the matrix. Being north-up, when you apply the geotransform, you are specifying something that is based on the matrix order. So the matrix is exactly opposite ordering in respect with the north-up image. And so to simply to express this concept, the geotransform, the affine transformation, the geoaffine transform, the affine geotransform, express this by using the minus in the vertical resolution, and it's simply used to maintain order in increasing and decreasing the coordinates. In respect with the GDOL geotransform, the rasterio geotransform can also be used to simply find the geographical coordinates starting from pixels. In this case, dataset transform, for instance, for the pixel in the left up corner gives you the coordinates of that pixel. So this is simply the user of the dataset transform to get the geographical coordinates. And you can also do the same thing on the opposite corner. So here I'm using the width and the height of the image and get the geographical coordinates of that point, also the opposite corner. Essentially, you could also do the same thing. You could use this notation to do exactly the opposite. So C 6.0 and 50.0 should give you exactly the row and column starting from the geographical coordinates. So this is a useful function, a useful functionality of the raster transformer, which is not available, for instance, at the GDO API. Other main methods are index and XY. They are properly used to perform the same operation in a more conventional way. So in this case, index is used to get the image coordinates starting from the geographical coordinates. And the opposite you will do by using XY method. So you are passing the longitude and the column and the row and the column to get their geographical coordinates. You know that generally speaking, all geographical coordinates are always expressed in terms of longitude and then latitude. But in the case of matrices, the order used is exactly the opposite. So you generally specify row as a first coordinate and column as a second coordinate. Another useful method is the CRS that is simplified here. CRS express, in this case, the EPSG code of the dataset, which is 4327, the common WGS longitude latitude system. And even the dataset shape, that means a list including the number of rows and the number of calls of the dataset. In this case, again, there's only one single band. So you can see just two coordinates. A synthetic definition for the dataset is also the so-called meta information, the meta variable, which is a dictionary that includes all information known for these datasets, including its driver, its data type, the no data specification, weight, age, number of bands, system, coordinate system, and again, the transform. This is useful because when you read a dataset, you probably are also interested in changing something in the dataset, so processing that and writing the result back. You will use the meta variable and change that just and use it after changing what is needed in order to write, and we will see some example after this part. The data types includes, of course, is again a list. In this case, there's only one data type that is a 432. Again, this is a list because one could expect that the dataset includes multi-bands. So generally speaking, Open is able to manage both multi-band and single-band data. So talking about bands, what are the bands? The bands are objects that are managed by NumPy. NumPy is another numerical, it's a numerical Python a well-known package that is used to work essentially with any kind of metrics or numerical matrices in Python. In this case, the method indexes express the number of number of bands included again in the dataset. So under this regard, this could be a list including the number, an index for each of the dataset band. In this case, when I read the dataset, I'm reading just the first element, the first band, because it is the only available in this case. And so I can specify when calling read the index I'm interested in. When you write this, when you read this data, this band, you get in a few the NumPy object that is a matrix of all information included in the band. Note there that in this case, I'm also reading -9999, which is the no data information. So this information is included in the resulting NumPy array. Again, I can at this point access each of these elements by specifying its coordinates. So it's xy, it's a row and column. So yx. This is this element, which is this one, and the successive element is 0, 1. That's because NumPy array are accessed in C-like style, so rigorously in row then call. When you will access multi-band data, you will access specify the band, then the row, then the call. If you have a three-dimensional information, you will have the first dimension, the second dimension, the third dimension specified exactly as in the C-like order, so never by column. So this is the second element. Width and date are specified here. So this is the number of columns and this is the number of rows. And this is the last element accessed. This is this one by using exactly the call, the number of calls -1, the number, of rows -1, and the number of calls -1. So all pixels are accessed in NumPy array starting from 0 up to the number of rows -1, and again starting from 0 and the number of calls -1. So all indexes in this kind of array are named starting from addressed starting from 0, not from 1. That's because these are C-like matrices, C-like arrays, not Fortran. There's
Yeah, Francesco, I think in the moment that you open you create a band, is in that moment that the data set enter inside, I mean, the full matrix is loaded into the RAM, isn't it?
Right.
Okay, before it is, yeah, before it's not yet in the RAM.
Yeah, I just I just opened the data set, but not accessed any data there. I need to read explicitly the band. We will see that it is also possible accessing just a part of the raster by specifying a windowing size. So I can do that. I could also access to a window taken from, but we will see an example after this part. So not necessarily need to load all raster into memory. This optionally can be done, but it is fully optional. So I was here, I think, yeah. One secondary package which is useful in some cases, you should think that as a basis, Python is think as a language for processing, it is not a GIS. It's a language used for processing, and you are also interested sometimes in visualizing your results. But typically, what you do is using an external GIS to access those data. It is not necessary. Stereo and other packages that are often used in Python, that is matplotlib, for instance, are often used in the notebook context in order to visualize raster and multi-bands, or raster or single bands raster. There are a lot of different limitations because it is not so complete for visualization. They are not interactive, for instance, like it happens with other languages, well-known languages, well-known for having interactive sessions when visualizing graphics. But that's because essentially the Python language is used only for processing, not for visualizing. In this case, anyway, raster plot is usable to visualize and giving some basic information, some basic meta information, such as the name of the raster I'm using. One can also use some additional options to use, for instance, a color map, a different color map compared with the default one. But this is not of current interest of working on that. So, just for example, you can plot the data by using plot show and the band, or you can also plot define its extent in geographical information, or you can also plot an histogram, a simple histogram of the band. As we'll see, as we saw before, when you read the data, you also read the no data altogether. And this is evident in the histogram. Here I specified 100 bins, and you see that this is the no data part of the band, while this is the other, the proper histogram of the data. So in order to read, taking in consideration the masking, and so avoiding to load also no data pixel, you need to specify that at read time by using masked equal true. The default is false. So this is the easiest way to load only very significant data and not also no data as part of the matrix. You note that in that case, the masked array, which is loaded, is different from the previous one because it has also a mask array included with this load. So these are the data, and this is the mask where you during the visualization you see that the matrix is loaded as in the previous case, but this is also loaded a mask array that include Boolean values for pixels that are valid and pixels that are not valid. So you are increasing for sure the memory footprint. Yeah, Giuseppe.
Yes, and every time that we are going to use this band, we need to specify the mask, or is going to be getting automatically? So
It
if
is
I want to
taken in
do it
consideration automatically. You
automatic,
load
so
in this way because the mask now is available for the processing, so it is all fully automatic. So indeed, I'm repeating the showist, in this case on the band taking in consideration the mask, and now the histogram is the correct one. So it is automatically taken in consideration. One could also be interested. Yeah. Another question.
Yes, I have a question about the loading the data. And this time you didn't use band 1.
Yeah.
While the previous time you had specified that. Why is it different?
Okay, yes. Without specifying the one, you mean that, right? That,
yes, exactly.
Yeah, it is that in this case it is fully optional because there's only one band. Anyway, we will see that when you read without specifying the number of bands, it will load all bands.
Okay, that's what
we will see that in a few.
All right, thank you.
Per default, it will read all available bands, but if you specify by the index of a band, it will load that index. So I'm alternatively using the explicit index or not. In this case, again, I'm not using. I could use one or not. An alternative way to take in consideration the node data, and this could be useful in some cases, is by specifying the mask after the loading. So here I'm using a NumPy method, the NumPy MA masked array, to specify the masking data, the node data, by specifying this node data after the loading by rasterio. So here I'm saying that if the value of the pixel is minus 1999, then this pixel is masked. So the mask is something that is specified in this case by clarifying what is the node data pixel. This is useful when the input data does not declare the node data value, which could be the case in many cases. It is possible. A lot of not valid data are often distributed with 0 instead of node data, with the node data not specified, and so on. So you can always specify before, after loading the data, if things are weird, and so adjust your data for your requirements. Of course, you could also, because the node data specification is purely a metadata information. So you could also alter your data set and adding a node data specification in any case. You could do that simply by using a GDAL tool, such as GDAL edit, and so specifying the correct, or later, I think there's a question.
Yeah. Oh yes, thank you. I was just wondering why do we have that separate line with band underscore masks after creating the mask before showing the mask?
Oh, that's wrong. This the plot. That's yes. This is perfectly. You mean this?
Okay, thank you.
Yeah. So the plot show that is in this case again the mask is taken into consideration.
That line band underscore masked. So that one is done by NumPy, isn't it?
Yeah. Okay. It's external to rasterio. You are specifying the band, the mask in NumPy.
Okay.
And indeed, we could, for instance, add you could specify the moment. So I've added masked. Again, you see that it's exactly the same thing. So this is a characteristics, this is a feature, sorry, of NumPy. It's not a rasterio proper feature. Adding the mask is a feature of NumPy. So you are simply using that feature to manage the bands.
Okay, thanks. And just for everybody, I hope that you can see a lot of similitude and links with what we see so far with GDAL edit, the property of the GOT, the masking operation, and so on. So this is a good bridging that we are talking about the same data set, a way of computing, but under another programming language. But you can do this similitude and so on. So it's very good. Yeah. And now
that's the data model of GDAL. You should consider that in at the origin of the GDAL library, Frank Wobbemeyer had to define a data model for any kind of data. And so GDAL defines his own internal model, which is called the GDAL model, to express any type of geospatial information, both for rasters and for vectors. Then the driver used for every format supported by GDAL tried to map this internal model to the external model supported by the vector format, for instance, a shapefile, or by the raster format, for instance, a GeoTIFF, which is not necessarily at the same level of the expressivity of expression of the GDAL internal model. GDAL internal model could be much more rich in respect with what is supported by some driver, some format support in the GDAL library. So the general GDAL model is that is in consideration and taken in consideration by the raster, which is a superset, I mean, of the raster, of a generic raster model. Now, just for an example, we can, in this case, create a multi-band image by, I'm now taking in consideration these three files that are GLAD, hard, SVVI, I think mean, medium, and yeah, they should be three in a way. Yes, three different models. And I'm creating a virtual raster supported by GDAL. So I'm creating essentially an XML file which is called this VRT, making a single data set starting from 3 bands. I don't know if Giuseppe already shown this procedure from GDAL. But in any case, you can always create a multi-band file by linking together other files in whatever order you like. So the GDAL BERT is quite instantaneous because it's only the writing of an XML file. It is this one. This is in a temporaneous area. Now I can open this data set and do a read. In this case, a read has a different shape because we have 3 number of rows and number of columns. So in this case, I read all data set, the whole data set. This is 3 bands, all of the same dimensions. So this is our first multi-band file, and we can again use the plot show to plot this image. In this case, you are specifying simply the natural order. You are using simply the natural order of this band. So you are using RGB for the first 3 components. If it was with multiple bands, you have to specify what are the RGB components to use for creating this result. And note that when you run a plot show, it also rescales the data. So for integers in the range of byte, and for floating point in the range from 0 to 1. So it normalizes before showing the final result. Now it will take a bit, and this is the result. Sometimes it's also useful changing the natural order of a stereo. That's because this is the reason to have this method reshape as image, because some packages in the Python world works with a different order. So the reshaping is used to change the order of the NumPy array in terms of rows, calls, and number of bands, which is the opposite in respect with the natural one. So here the shape is different from the previous shape. This is the natural shape from rastereo, and this is the different shape used by some packages. So there are a couple of different methods. One is reshape as image, and the other is the opposite, reshape as raster, to change the order in the NumPy array. It could be sometimes useful in the use of rastereo. Now, again, we create, for doing a simple computation, we are now creating a simple NDVI computation. Again, in this case, I'm using build-virt separate, creating a Landsat combination by combining those files that are available in your virtual machine. They are at this location. This is part of a well-known dataset from GRASS.js. This is a Landsat image, a small, quite small Landsat image. The Landsat in this case is distributed in terms of 9 bands. That's because the thermal bands is divided in the low part and high part. So instead of being of 8 bands, it is distributed in terms of 9 bands. But for our use, it's perfectly the same as the standard one. So again, I can use open to open again in read-only mode in NumPy arrays those bands. You see that here I'm using, so let me create the raster anyway. Opening it, and this is the Landsat, this is the NDVI computed on the image by taking in consideration band 4 and band 3. Again, the band are numbered starting from 0. So I need to use in practice band 3 and band 2 and computing the NDVI. Note that I'm using here the masked to avoid the non-valid pixels. And I'm using a simple matrix notation. That's because I'm not specifying any for loop to computing the NDVI. I'm simply using the bands as in a normal calculator for of a GIS or any other kind of high-level language matrix that is able to work with matrices such as MATLAB or IDL or any other which you can know. Just to check, I'm printing min and max to verify that it's in the right limits for NDVI. This is the shape of this data set. Again, with 9 indexes, so 9 bands. Now I'm interested in writing out this NDVI data, and I'm using the so-called profile. The profile is nothing else that the meta information of the Lancet dataset I created. Here I have to change something because I'm starting from a VRT, which is a virtual dataset. I'm now interested in changing the output data type. Note that I started with an int32. Now I need to change the data type in float32. And the output will include only one band, so count is equal 1. The driver we'll use will be a GeoTIFF thread, so not writing a VRT, not more a VRT, but a proper GeoTIFF. And this is the resulting profile, where indeed I changed just those information, all the rest is the same. And this is the open in writing mode. In this case, I'm using the name I will use for the output. I specify the mode write. I could also use write plus to say I would like to write and then read again the file. Let me execute anyway those lines. So what I'm doing here is using a profile. This is one of the optional acts I can add to the open call, because I'm specifying the profile to use, which is different from which is based on the input one, but changed with all required field I need to change. And this is the single write out of the Rasterio band. In this case, I'm specifying that NDVI, which is again a NumPy array, need to be customized, custom to float32. This is for safety, in order to avoid to use some double precision instead for the output type. And of course, this is the band number 1. Once I did that, I can also show the NDVI again with a regular standard color map. What I can do here is also, for instance, seeing if I can mask out part of output a mask where I take in consideration not vegetated area, what I call urban areas. In this case, I'm using the already known masked array and specify that the mask will include will be masked out all parts that are that have an NDVI greater than 0.6, which corresponds to a threshold useful to filter out the vegetation. And so this is the histogram of the final result. So taking into consideration only the part that is urban. And this is the final visualization. This image is include essentially less vegetation area, less vegetated area, and more urban areas in this case. So other useful information I can get from this NDVI could be, of course, statistics such as a mean, average, the mean, the max, standard deviation. Note that, for instance, if I'm interested in NDVI median, I have to use a NumPy method. So sometimes the API or the packages are not totally consistent. One would expect the median as also a basic statistics for the NDVI in this case, but it is instead not a basic method. You need to use an external package to an external sub-package MP, so a NumPy mask to work on with these statistics. That's to say that not always the API of Rasterio or NumPy are completely consistent, even if those packages add years of life. It is not always completely coherent. Sometimes something needs to be adjusted, or you have to use some tricky method in order to compute some information. So here I'm doing the same thing on the urban layer. There are a little difference among them. That's because the no data areas are quite limited. Now, another useful function of Rasterio is that it supports directly the possibility to use vector to mask rasters. So you have not to require to use anything but simply one of the sub-packages of Rasterio. In this case, what I'm doing, I'm creating a GeoJSON vector. I don't know if the Giuseppe talked about GeoJSON.
Not really. You can say a few words. We didn't counter it yet.
Okay. GeoJSON is a format that is now, it is a standard format. This is the basic. This is basic observation about that. The GeoJSON is quite useful in front-end contexts. So, for instance, it is very often used in WebGIS. So it is quite used in many applications. All languages like JavaScript and so on generally use a lot GeoJSON vector format. It has less limitation in respect with the shapefile, for instance. You should take in consideration that a GeoJSON is simply a text format like this one, where you specify all meta information. In this case, this is a simple polygon, and you ask, this is specified by using simply coordinates and specify what is this G-code and a few other information, nothing special. This is a very compact format, often used to describe even quite complicated geometries in a very compact form. It is, in the last 20 years, I think it's much more used than other formats because it is compact enough and it also readable by humans, at least a lot of them. So in this case, I'm creating a simple JSON file by simply using a cat in dumping this description, which is of course also a legal dictionary also in Python syntax. This clip JSON, this is a JSON format as expressed here. This is the result of using OGR info on this file. So very compact. This is OGC expression that describes the single polygon here included. It is possible to use one of the sub-packages of Rasterio in order to create, starting from the GeoJSON, so starting from vector, creating from scratch a very simple mask, which can be used to, for instance, to clip out, to crop the image, the landscape image we used before. So Rasterio.mask and Fiona are useful because I need to use Fiona to read in the GeoJSON and extract the shape, the only shape, just one feature. The shape in this case is a list of a single polygon. So the type is polygon, the coordinates of the polygon are this. I don't know if Giuseppe already, Olaitan, you are probably waiting for doing a question. Maybe not.
Maybe not anymore.
Sorry.
Yeah.
Yeah.
It's
Okay.
you've gone way past it. It was that line where you did sorry, on the Landsat where you did the band 3 plus band 2 and so on, and you did a masking before that. So I was just wondering. Sorry for taking you back.
You mean this one?
Yeah. So you did your maths first, and then you used the band in mathematical operation. I was wondering that is it possible that in some situation after you mask, you wouldn't have the same number of node data in different bands, right? So you might have, let's say you have 10 pixels in band 1, and then you have 10 pixels in band 2, and then you have maybe 2 node data in band 1 and 5 node data in band 2. After masking, you don't have the same number of valid pixel, and then you
Yes,
do this
this is
mathematical. Can that be a problem?
using only the simplified use of the masking. That means when the band is masked, or any of the band is masked, the resulting expression is masked.
Okay.
This is the which is also you could also do something different, but generally the default expression is in these terms. So whenever you have a mask, you have to get a masked pixel as a result.
Okay.
This is also this is also true in the case of, for instance, MapCalc in GraphGIS or any other generally band calculator.
Okay.
That's okay for you?
Yeah. All right. Yeah. Thank you.
So let's return here. I was here, I think.
Yes, we have Fiona.
Yeah. So this is the polygon as a single feature. Now we can use raster.io mask the package, and the method there is called mask again. And now using the input image, which is the Landsat multiband data. Note that here I'm using a SAT, which is the data set. SAT, this one. So I'm using the original LSAT. So I'm using not the bands, but LSAT data source. Okay. And then specify the shapes. You know, shapes can be any valid vector. So you could use multiple polygons, you could use points, whatever you like. And I'm also asking to crop the final result. That's because if I do not crop, which is the default, the resulting image will be exactly of the same geometry of the starting of the input. So in this case, I would preserve the geometry, but I'm interested in crop the image. So I'm using a polygon to clip the image and having a final result of the reduced dimensions, the reduced size starting from the input. In this case, this is the reason why raster.io mask.mask, the mask method returns always a clip image. So this is our results, but even a clip transform. That's because I'm changing the transform matrix. This is a cropped image, so I'm using another, not the initial transform, that of Lancet SAT data source, but a new one. This is required. You have to use a different clip transform when you write the image. This is the shape. Again, it's 9 band, and the size is this one, which is different from, I think I printed out before. Yes, it's different from the Lancet band's shape, the original one. And this is, I was here. This is again the meta, so the profile of the original image, which is, I remember, is a virtual with, again, in32 and so on. This is the original transform. Now I'm again updating the meta, the profile. You could use a SAT meta or SAT profile for the same reason. Yes, Giuseppe?
Yes, so in this case, you are creating the clip image and also the clip transform.
Yeah,
isn't it?
exactly.
And every time that I'm going to use the clip image, the clip transform is going to be read in automatically or so.
Yes,
No?
exactly.
Yeah, okay.
Yeah.
And the clip transform, they use they are the metadata.
Yeah. Note that I'm using now clip transform in update. So I'm using again a new driver, GTIF, and I'm using the width and height of the original image.
Mm.
Remember that shape 0 is the number of bands. So I'm using shape 1 and shape 2, which are the rows and columns. Sorry, the columns and the rows, the opposite.
Okay.
And now I'm using the clip transform I returned from masking. And now this update is enough to get also write the original profile. Which is this one. Sorry, the new profile, which is this one with GeoTIF in 32, because I'm just clipping the image. I'm just cropping the image, so I'm preserving the data type. I'm preserving the new data. These are the new dimensions, the new sizes. I'm preserving the system, the reference system, and this is the new transform. Then I can again write out the raster by using the new profile, and I write a clip image, which is not a single band, but is a 9-band image. So I'm using a single write to write 9 different bands. And the final shape is for each of this data raster is again this one, number of rows, number of columns. I'm now reading again with taking into consideration the masking. The result of the reading is again a 9-band with this size, and this is the final result, because this was a simple clipping polygon within the Lancet image. Okay. Any question? Any other question? Oh, note that at this stage, all files I created are directly wrote on disk. They are all present on disk because this is a feature of the notebook. So you are the raster in this case. Every time it write out data, indeed the buffering, take in consideration this and write the result. You can always mix together, in this case, writing and reading operation, because all operation on disk are taken in are done without with the flashing of the buffers during the I/O operations, which is essential for our result. One of the most interesting feature of Rasterio is the possibility, I said that before, to using Windows, and so working on just a part of the data set. In this case, I'm using subpackages which is Rasterio Windows, I'm defining geometry, so I'm taking in consideration only 100 times 100 pixel. Sorry, well, maybe I use the wrong, this is 0, not 10. So I'm using the window in when I'm going to read. So the dataset is again open in conventional way, exactly the same. I'm reopening the same file I created before, but I'm loading only a part of the image. So with the geometry, a window, the first two coordinates are the offset in respect with the 0, the origin, and the other two coordinates are width and height of the window to consider. So in this case, I'm using only 100 times 100 window taken from the original data. So the window is specified simply during the read, and again, I'm reading 9 bands because I'm not specifying the number of. You should consider that here you could use a number for the band, or use the array argument. It's completely indifferent. Okay. Let's run this part itself. Open. And about that, of course, that influence the transform, the geotransform again. So when we read a windowed matrix, we have to take in consideration that when we wrote that matrix, we have to take in consideration the new geotransform, because geometry is different. And indeed, there's again a useful function, which is window transform, which on the basis of the wind definition I used, give me the new transform to use for an eventual output file. Okay, this is essential because if I read in windowing mode, I have to write in windowing mode and cannot use the same geotransform as an input case. So this useful function with the transform to do exactly this thing.
I'm sorry, can I ask a small question? What does these parameters after the affine this function, what is the meaning of these parameters, these numbers? Are there some kind of spreading or rotating of image like this?
It is a roto translation. It's a roto translation specified that specifies the map from pixels in the geometry mode. So from number of rows and from rows and columns to the word, and the word is in your reference system. So in this case, I think this is a Lambert projection, and so it is a planimetric projection. And you have to specify a roto translation for that.
Because our data set, our object win, is just a matrix in the beginning without any geolocation.
Yeah, exactly.
Okay,
so the geotransform is expressing is linked to the CRS, but it needs to express essentially where our matrix is located in the world. Of course, it has to take in consideration the resolution, which is present in the 2 directions, and also where the corners are located. This is one of the way to express this kind of relation between the word and the plane. It's not the only one. As I said before, you could use ground control points to do the same thing, or you could use rational polynomial coefficient to do exactly the same thing. What it will change will be only the number of coefficients to use. This is the most compact way to express this relation between plane and word. to complete this part and then take a pause, I think. Take in consideration also that when you work with the GDAL model, often the format behind the GDAL specifies some kind of block factor. So, for instance, in this case, I'm looking to the shape of the block shapes again on the data set to see how the original data set, which is again the source, this one. The source is this one, the clip in this case. How it is written on disk. Indeed, these 9 bands are written in blocks of rows. That's because 253 is the size of the column, the number of columns. So basically, all bands are written row by row, and so the basic factor, the basic block size is the row. Often, when you work in windowing mode, you should take in consideration that if you use the block size of your format, it's for sure the most efficient way to work on the file. And so you should use possibly that block size to create your windowing and working in the most efficient way. Okay. Questions?
So in that case, in our case, in this case, the block size is 252.
250, yeah, 253, yeah. The size of the length of the row.
So just one row. Yeah.
Yeah, it will change on the basis of how the file is organized. Essentially, it's a choice of the driver.
Okay. Yeah.
So we can take a pause. More
Yes.
information, example, and documentation are here, which is the complete documentation in for Rasterio. Now we will see in the next part the Raio tool and also some practical examples of use of Rasterio on the part on the data set that Giuseppe described in the first part. So we can stop for
perfect. So we
20
come
minutes.
back. Yeah, we come back to 45. Yeah, we come back to 45.
Okay. See you in a few. Okay, I'm still in. Okay, I'm still sharing. One quite recent part of Rasterio is the so-called Raio tool, which is a command line tool which can be used to perform some complementary operations, especially digital tools and APK tools. Again, even about that, not always all things are completely complementary, or you can often do the same thing in alternative ways using one or the other tool. Always, all those tools are in continuous evolution. So you could find that when you use a script with a certain version, which refers to a certain version of the Raio tool, you could find that something can be changed, or even you can find new subtools you can use to change your previous scripts and do something better or in another way, alternative way, irrespective with your original formulation of the problem solution you find by scripting. So this is of course the Raio. The Raio tool is installed under your own local/bin directory folder. If you that's if you install Rasterio by pip3. Note that you should always use pip in non-administrator mode. So you should definitely have this tool installed under local bin. If you call the Rio tool, it will return this help, this useful help. Just a bit, because it has to load quite a lot of sub packages. Just to have some idea, you can use it to clip raster, to convert and copy data set, to edit again metadata information. You saw that a lot of metadata information comes with data sets, and you can change all of them. You can manipulate also the ground control point if your dataset includes them. You can also run in essentially in debug mode or in development mode an interpreter, a Python interpreter that already integrates the raster IO, and you can work with the source with directly an interpreter. You can manipulate again masks, stack also multiple bands. One useful function is the delete of the data set. That's because often data sets formats comes with the so-called sidecar files. And so when you remove a single file, you are not removing the whole data set. You are removing only one component of the data set. You should think to, for instance, an MD file. And the file comes with the data file and the header file, and possibly also other add-on files such as pyramids, for instance, and many other. So the remove function is a useful add-on for that. We will use in a brief the sampling feature of the Rio, and so on. The transform coordinates are available again, and you can also warp, as in GDAL warp, the data sets. So, for instance, you can see in JSON format, in GeoJSON format. This is just an example. The bounds, so the bounding box of a raster file or a raster data sets. It gives you the result as a useful GeoJSON file. So it is a valid geometry for OGR, and so it can be used in other passes of the audio processing. One useful but quite recent feature is the so-called calc. So Rio is also able to perform some computation over the raster dataset, but you have to use a quite original, I would say, a quite original syntax, which comes from the so-called snacks package, which is now part of NumPy. Unfortunately, it is not spectacularly documented in the raster.io documentation, but essentially it works as such. For instance, this is an example. You are using a Lisp-like, for people that do not know about Lisp. Lisp was and is one of the first language used in artificial intelligence application in the I think in the 60s, it is quite strange for the syntax, for the unusual syntax, because it is list based. You should think at Lisp as a sort of list calculator that works by using operators and operand in this quite peculiar format. So in this case, we are doing a sum. I'm reading the first band from the file. In this case, from the DEM. I'm multiplying. So this is the operator. It by 0.95 and summing, and this is the other operator, to the result. The final result. So it is written to the output file in this case. That's quite peculiar. You have quite a lot of different operator to perform a simple operation over multi-band files. If you are curious about that, you can find information in the code repository for Snags, which is now part of the BI, and can be used to perform operations that are basically very similar, but also extend those of the calc utility of GDAL, and possibly also of the PK tools. Operator includes mean, average, so max, and so on. All usual operator are expressed herein, and can be used to perform a lot of different calculations. Now, in this second part, we will see how we can prepare for the next part of the machine learning exercises, the data that, sorry, Giuseppe, you asked for
yes,
something?
but
I'm losing
syntax
you.
operator.
Repeat, please.
So why sometimes they have these, they use these Lisp-like language notation?
That's quite a good question.
Once I was using the Polish inversion notation, I get
Yeah. It's something
frustrated.
like the polishing notation. I don't know really, because the snags, there are some the usual problem is that often people likes to reinvent the wheel. so often,
it's not a computational needs that are fast.
No. I think it's essentially a compact way to perform operation. The Polish notation is one of the alternative ones, but of course the Lisp one is quite known because still a lot of people works with Emacs as an editor, and Emacs uses Lisp, and Lisp is used also in other contexts. So they are simply taking in consideration this availability, this knowledge by other domains, and try to use to be consistent with this knowledge by using Lisp. I don't think it's really a problem with, for instance, performances. Of course, when you perform calculation, you need to find a compact notation, and something that would be quite easy to parse and convert in interpreted language. That could be one of the reasons. So you have to work with a stack and so on, and operators in order to work in the most simply way to avoid creating too much complicated parsing rules and so on. I think this is the main goal of those kind of exercises in creating a new computational tool.
Perfect, thank you.
Okay, the notebooks that will be used after this part of diving in the data are the create notebooks that are present in the usual area. We will perform some simple operation by using two different approaches. One is based on rasterio and the use of show and bash in a different way. And the other is based on simply writing a single script that do all operation in one single script. And we will see how all that can be challenging. So this part, I think, is already done by each of you. So the downloading and so on. If you have a look in the create.txt part, you will see these 4 files. Specifically, there are one file that is this one that includes simply a long list of coordinates in longitude latitude form. Here I'm presenting just the first 10 rows of this file. The true problem is that it's a 1 million of coordinates file, more than 1 million. And so basically our goal is to create this file, this UXY predictor select.txt, which includes exactly the same list of 1 million and more coordinates, prefixed with an ID. So this is, each of them is a feature. What we are interested in is taking in consideration all these files, all these georaster files that are 19 of them, no, 21 of them, and taking the value of each of this file at the selected coordinate and join all the values taken at the same coordinates on the same row. So basically, this is a CSV file with a long list of raster data associated to the same coordinates, longitude and latitude. Again, these are only the first 3 lines of these files. That includes, again, more than 1 million of rows. So our exercise in this case is simply using the first file to get the values in the right at the right coordinates from all the other files. Of course, this is nothing new for you. Note that here there are also a couple of latitude and longitude files, but these values are for sure also included here in the input file on the select. So among those 21 files, we have to take in consideration only 19 of them, excluding latitude and longitude, because they are already available as a value in the input file. So all these can be done, of course, by shell, and you could also use multiple tools to perform exactly the same exercise. We will see how we can do this by rasterio or by RIO file, by RIO tool, but you can also use GWlocate, sorry, to perform exactly the same operation in a compact way. So we can approach both the idea of you creating a single shell script to create this new file, or even using a single Python program to perform exactly the same operation. So let's see row by row what I'm going to do. Again, this is also this is all of them are done in all these lines are written in simple shell tools. create txt u xy select txt is the one of our input files that includes the coordinates. Now I need to manipulate this file in order to get this format. So what I'm doing here, I'm changing the simple list, this simple list of coordinates, adding comma and brackets at the start and the end of the line. Why? Because I'm going to use RIO, and specifically RIO sample, this one, to sample each dataset. That's because if I use RIO sample and give RIO sample this input, I get for each file this output. So again, within a bracket, the value of the selected dataset in that point. So RIO sample is simply getting exactly the same result of GDALLOCATE to get from each file its value in the selected coordinate pair of coordinates. I don't know if you already know SED, but SED is also called string editor. Is a simple tool to manipulate string in input and get output starting from what is called the so-called regular expression. So specifically, I'm saying here in this part, taken in input the rows that are the number, the longitude, space, latitude, add. Replace space with a comma, and then replace the start of the line with open bracket and the end of the line with close bracket. And this is the final result, line by line. So I'm doing exactly the same thing here, and I'll put the result. Okay, again, these are the first 10 rows of the result. Now, basically, one could use RIO sample or GDALLOCATE to perform the same thing. And basically, one could also use RIO sample to perform exactly the same operation on all rasters, but for a problem that is all rasters are separated, and I need to perform the same operation by stacking, ideally, all raster in a single raster, so in a multi-band raster. But we have a problem because RIO stack does not support multiple data types, and the same problem is true also with UDAL-BERT. So you can't stack or create a virtual for multi-data type files. And for that, so ideally, one could use if this limit was not applied, if this limitation was not existent, one could use RIO sample to simply sample a list of rasters in a single pass, but it is not possible currently with RIO sample. So we have to arrange something different. See here, ideally, if possible, one could do something like this: RIO stack, taking in consideration all the file, removing latitude and longitude among the list of the file, and creating a final multi-band, including all those files. If you tried to perform this operation, it will fail because that is not possible. And the same with GWVert. That's because the files cannot be. Oh, this is wrong. One has to use this. So that's not possible. So we have to write a simple, a more complicated script like this, for instance. This is a bash script. We have to take in consideration the list of files, excluding latitude and longitude diff, and then create the header file, the header that we will use for the file. The header will be created by using this part, this for loop. In this case, files includes all the flight that to take in consideration. We have to drop the extension .tiff, and we also to drop the first part. If I try to perform this operation just for clarify, no, not copied, sorry. Okay, this is the list of the diff file, which includes 21 files, but we have to we include also, let me be less compact. We have also included latitude and longitude. So one way to avoid this is removing these two files by specifying latitude or longitude. Okay, and this is a list of 19 files that does not include latitude and longitude. This is the reason to use this trick here, this one. And now to create the header, so we have to append to the header each name of the file, each of these names, ignoring the extension and ignoring the directory name. Okay. So header is created, is filled in with the name of the file and using the space to separate one name from the other one. Then this is the code that we use to perform a RIO sample and create the resulting temporary file that includes all values of the chosen raster file in each of the coordinates included in the select file, the select.txt file. Okay, so in this line we will create a unique field file in output that includes all sampling in each of the coordinates used in the input file we use for the coordinates. At the end of the loop, we will have one file that is sampling each of the raster in the coordinates we selected. The TR is used to remove the brackets in the output, this one. Okay, Finally, we need to provide also the ID. So the first column of the file, this one. The first column is simply a sequence of number from 1 to 1 million and 200 and to 1,002,000 and so on rows. And this is done simply by using this other tool, sec creates sequence. Let's see how. Okay, so this is the result of calling sec. We are simply counting the number of coordinates of pairs within this input file, and sec is a simple utility like that. They do something like this: counts from 1 to 10. So it is counting simply. It's the same to this one. So it is simply creating a list of IDs that we need to prepend to the column. So finally, we are creating header that includes the name ID, the ID field, the X field, and the Y field, and then the name of each of these files. Output to this temporary file. And finally, we use past, that is another tool that concatenates files, to pass all together all those files created before. Or each file includes the sampling of each of the raster, the input raster, in the set of coordinates. So this is the input raster. These are the input raster. This is the input coordinates we use for RIO. All of these files, text files, are then concatenated by using past. Each column is separated by one space. So as you can see, it's quite tricky. You are doing something simple, that is concatenating the sampling done in each raster file, its coordinates, but it is quite tricky. So this is the tricky because you need to use RIO sample. You need to perform strange operation like using SED to manipulate the input and convert it in a format which is usable with RIO sample. You have to manipulate the output to add the IDs and so on. So the final result can be get by using simple show and a few other tools. What is the weak part of all this approach? If you return in 3 months to this to this shell script, you will not understand what we were doing, what we were doing to perform this operation. That's the tricky part, the problem of this kind of approach. And so this is also the reason why most of the programming languages like Python basically was born in the principle, and not only Python, but also quite older languages like Perl or SQL that were used in the past. Avoiding to use too much tools, external tools, to perform simple operations that are quite tricky to concatenate all together in a shell script. I hope to give some ideas about why it is much more productive using instead a single script. Now, because it is much more clear for the human beings this is the region to have a language that is able to synthesize your simple algorithm in a single language, much more readable. Yes, Rosie? You did not understand anything, probably.
No, it's actually a question about the data. So I've been following along what you've been doing with this intro script, but when I go looking for the txt files that are used at the very top of this script, I can't seem to find them anywhere. I know a couple of other people are having an issue with missing data. Did we have to do a git pull specifically before this data was included?
Oops, everybody's not following Mattermost. I pasted in Mattermost what to download yesterday.
Yeah, so I think
Maybe. So we need to do this.
Please use Mattermost because I use it. I think you should
Okay,
also receive an email when I post in Mattermost.
Yeah, so I downloaded it this morning. I saw your message this morning and I had it downloaded before we started.
Perfect.
No, I haven't got any emails, but I know that I need to look at Mattermost, yeah. But no emails, sorry.
But
I will double check because it should be appearing every time that I post something. It should arrive to you as a email also in Mattermost. So if you go in the beginning of the script, you have the G down.
Yes, there's the Google Drive download.
Yeah, so
the very first part, this one.
Yeah, so I did that this morning and I checked the whole 3.6 giga downloaded successfully.
Yeah.
And I was able to, so I'm following along on my laptop with the notebook raster IO. But when I try and run the commands in the notebook, it's telling me that that there's no such file or directory.
This one?
No, so in line 7.
So it could be that is depending from where you start the Jupyter notebook.
Yeah.
Okay.
You should stay here in this directory.
Yeah.
And everything. Yeah. I think it's due to the path where you started with the Google Drive download.
Okay.
Yes, and I'm sorry, and I'm can even find this raster IO intro notebook. It's also should be downloaded from this, yeah, or
yeah.
Yes.
Okay, thank you.
I just downloaded it via Git just a couple of hours ago, not more.
So once again, every time this morning, do a Git pull.
Yeah.
Okay, enter in the SC data and do cd SC data Git pull. Okay. You should ask before, guys.
Right.
Okay. At least the Jupyter notebook. Then the data set maybe is a bit too long now.
Yes, it's definitely too long because it is more than 1 million of rows, so it's not practical. Even with this approach, which is based on shell, you need quite a lot of time to this one. With this script, you need quite a lot of time to perform this concatenation via shell. And we will see that all things can be done in a single Python script. I will explain how we will work using a single Python script that is available. I think it is available on the Git now. This one specifically. Oops. You see this raster IO final script, which is exactly the same that you see at the end of the notebook. Okay, this is exactly the same script. You could run this one, but for a couple of things. I should have one of this still now, probably not. Anyway, on this machine, it requires about 6 hours to work. Okay, so this single script. And you have to also increase the memory dedicated to the VM. This is a limit due to the size of the data set. Working with the virtual machine it was on so great dimension files requires that you increase the memory use for the virtual machine. Here I'm using a 16 core box dedicated for the virtual machine, and sorry, an eight cores, I think. Let me see. 16 gigabytes of memory, probably. It's run since yes, 8 core and 16 gigabytes of memory dedicated to the virtual machine. And note that now I'm not using more swap space, but during the work, this machine take almost 16 gigabytes of memory to perform this thing by a single script. Okay, that's due to the presence of the the notebook system, of the Jupyter system on the machine, but even to the number of rows to manipulate. So it is quite heavy for the virtual machine to work on this. Huh? Of course, on a physical box, probably it could require less hours, but in any case, it's not a simple task to perform because there are a lot of records. So what I suggest for to work with the script, and even this is also required if you use this script, this shell script. It requires a lot of memory because Rio samples need to manipulate these files. This is probably a relatively small footprint of memories because Rio sample works for each raster separately, but you have to collect all files and pass them together, so it requires quite a lot of time. With a single script, you can instead perform the same operation with Python, totally using Python without using any external tool, which is much more easy to understand when you have to read what we are doing. And let's see how. My suggestion is to install in the virtual machine this package, so swap space, which in case your virtual machine has a limitation for the memory space, could avoid that it breaks for the missing memory. Of course, the times of computing are quite long in any case, but you can get to the final result. Now we'll see, just for didactical reason, how it is all done. So we will use those packages: the CSV package, the globe package, the rasterio, and the OS path. We will start from collecting the required files, and so we use globe to create a list of the files that we need to work with. So files is a list initially, an empty list. By using globe, we get the list of all TIFF files, but for those files that starts with L. that are latitude and longitude. Then we use Rasterio to open each file, each dataset, and append these datasets to the files list. So files is simply this. Let's start from the start. So files is simply this long list of datasets. These are 19 datasets, 19 elements. If you have a look to OS base name, it is usable to separate the directory from the name of the file. So OS path base name function of files 0 names gives you the file name without the directory for the first one. Okay. We can split by using OSPath split the base name of the file by the extension, and see. So we get for name the required name. This is the field name for each of the first column of the final file. Okay. Then we can create the header, and the header is created simply appending each of the name to an initially empty string. And this is the result. Here I'm stripping the initial space because the first element, the first substring is this one, and so I need to strip the initial space. Okay, I'll strip just to clarify, but it is not strictly required. We can also work with without using stripping the initial space. Then we need, of course, to read each band for every file. For the first band, of course, we have this one. We are ignoring the masking in this case. We are ignoring the no data value. That's because we are collecting all values within the for each of the coordinates. We are not interested in knowing if the value is a valid value or a not valid value. We will have to filter it after during the successive phases. Probably in this case, this is the no data value for this raster. Then we have to repeat the same thing for each of the files. So we have to read each file and get to the final result, which are 19 of those bands. I will not run it here, just to avoid to wait that Rasterio will load each of those raster files. Then we have to concatenate by simply reading the select file, so the coordinates. This is a CSV files delimited by space, and so for each of the for each longitude and latitude in the coordinates file, we simply need to sampling by using index, the index function. We need to simply sampling each of the raster file and extracting the band value. So here I'm using index to get the IDX, that is the row and column list of the row and column coordinates, and taking in consideration each of the band I read in this phase. Simply taking in consideration what is the value for each of this band. Specifically, I need to use and empty value just to avoid the print issues. The print issue will simply append the end of line at each new print. This is simply a format requirement. Of course, all these produce for the first 10 lines, just for the first 10 lines, this result. So we are finally having the ID, which is the first of this index that is incremented at each step, and the coordinates, longitude and latitude, and then each of the value of each raster in the point I choose to get a value. Okay, this is just for the first 10 column. All these produce, of course, the result in output, but of course it's more sensed using instead a proper output file. So instead of giving the result as in an std out, so in the standard output, what I'm going to do is simply using an open here, this one, and create a new file that is AOXY predictor select new, where I append the header and then each of the long list of coordinates and raster values. So this is exactly the same, but with output to an external file instead of, in this case, standard output. Okay. So this would be the final result at 3. The first three line again, as in the previous case, at the start of the notebook, after performing these operations. So the final result will be, but it takes a lot of hours, quite a lot of hours. The final result will be exactly the same that we already have among the files. The original file is already available as this one without the new select.txt. So this is within the notebook, but you can run the same file, the same script, simply by command line. This is exactly the same file that is in this path. In order to use that, you could simply copy and paste this file and changing the executable bit on the file as explained here, and so one could run this file and get the final result. I think that Giuseppe already explained the use of this kind of the shebang line at the start of the file. I think so. Let me see. It is exactly the same, so it is used Python 3 to run all the rest. So a pair of questions. Hannah?
Yes, I have a question or an idea if the script takes so long, because I could imagine, I think we also have it installed on our machines already, like NumPy and Pandas, that you could modify the script to make it vectorized. So that it's
Yeah.
actually much faster, so that you
Yeah.
actually read all the bands into arrays and then create an array for the latitude indices and an array for the longitude indices, and then just stack the arrays and write that to file instead of having a loop. So maybe that would be faster.
Yes, that's the reason why generally those kind of languages need to be vectorized properly in order to avoid those kind of operations. You know, in this case, we are using in the most straight way the script by using the Python, by using for loops to extract the sample. The most effective way would be using a radio sample that properly vectorized, but we have the limitation that not all data at the same type. So there's a limitation in the radio sample, at least in the current version, because all that could be easily done by simply using the right tool vectorized once vectorized. So indeed, it requires a lot of time and a lot of what it cannot be avoided in is the memory footprint on those regards, because the image needs to be in any case loaded, eventually tiled, but that is not avoidable. So you have to dedicate, for instance, 10 gigabytes to the virtual machine in order to perform those operations. What you can get is a much more effective way to perform those operations, but also that's the basic problem that all those use of text file is not efficient in any way. So a proper way would be using directly binary files and using vectorized operation on those binary files. Instead, we are going to select coordinates and use those coordinates taken from a text file, a very long text file. And all those kind of operations are quite slow in any case.
Okay, thank you. Yeah, maybe at home I will try around a little bit. On some vectorized solution.
Yeah, that's good. That's good.
Next
good
time,
idea. Of course, you could also find that the vectorization could be done also. The efficiency could be augmented by using the pass system, the system of passing together the results, because you get the sampling file by file. That reduces the memory footprint, but of course in any case you have to cope with the use of text file, which is quite slow. In any case, 1 million of lines is not the same way of managing those data. That's the basic problem, and this is the basic problem of any LiDAR application. That's because generally LiDAR comes with with a big text files as a principle, sparse coordinates. And you have to work to interpolate in order to get a more efficient way to represent the information. This is a basic problem with the LiDAR. You have to cope with that. This kind of files are not specifically so large in respect with many type of LiDAR data. There are also other examples with the same problems. Anyway, all this can be done in a pre-processing phase in order to get a result in a binary format, which is more efficient to manage in subsequent processing. And we had also another question by Charlotte.
Yeah, this is maybe a more basic question, but I've been following along in the Jupyter notebook and running the cells as we go, and I'm getting a syntax error for one of the cells.
Well,
where you're doing a trial for concatenating the raster values. It doesn't like there's print and then open.
You mean in this script? Where exactly?
A couple up. This one, yeah, where the like third line from the bottom there, that print statement, is the B there a typo, or is that supposed to be doing something?
Oh,
The third line from the bottom.
Okay. Print. Oh, right. Yes, that's wrong. It's a
Okay.
B due to a type error in the cell.
Okay,
No, that's okay.
thanks. That's all. I just
Yeah,
wanted to check that.
In any case, you can run this script, which is exactly the same format, the same syntax used in the previous part, and you get the result. So, fact to have in consideration when working on those kind of applications. For sure, a single Python script could be better than coping with a lot of different tools and working on those. But for sure, this approach could be thought as a dirty and quick to get a final result in a straight way when any other possibility lacks. So you are using a lot of different tools to solve your problems without writing just another complete program to perform those operations. You just stock a lot of different tools to solve your problem, and this could be quite easy for many people to work with. Your big problem is returning and reading something that you wrote years ago and understand what you did, and could be quite challenging if you have to do that often. So better a single language is in most cases most effective on those regards. The second thing is that if you have to work with a lot of data, you need to take in consideration if your data representation is the right one for your problem, and not always is the case. Probably there's more than a way to represent the data in a more efficient way. Vectorizing could be a solution for the processing part, but if you have to cope with text files and with millions of records, probably the problem is in the data representation. So in the way you are storing your data, which is the wrong one, not the less efficient way to do that. So this is a typical use case where you can work to perform better and find a better representation of your data without going crazy to work with those information. And I think that is the final part.
Yes, Francesco.
Yeah.
I want to add also we presented in the in the GDAL we presented GDAL location info as an alternative to RioSample.
Yeah.
And actually I was just doing some testing, and GDAL location info is 10 times faster than RioSample.
Yeah.
Okay, so
that's because RioSample again is written a script, a package that is written anyway in Python. The GDAL locate info instead, it is always a not interpreted program. It is written in machine language and in C. So basically, for sure, it could be each raster sampling could be faster than that done in RioSample. So this is the basis, but remains the fact that 1 million of lines should be merged together I'm quite sure that I did not try with the shell versus the Python script. I'm quite sure that it's more efficient, the bash script,
Yeah.
in respect with a single script, at least probably for the problem of the memory footprint anyway.
Yeah.
But for sure, that could be done better by changing the data representation. In any case,
Yeah.
and for just to clarify, you know that Python is not known to be one of the fastest language in the West. That's for sure. Huh? You have to use vectorizing and extension in C to avoid being stuck in the dark with Python, and avoiding to have to wait days to get a result. But this is also true for other languages. Huh? Even with R and any other interpreter languages, that's the same problem.
Yeah, thanks, Francesco. And also, Francesco, point out that a new language is coming out in the last maybe 5-6 years. It's called Julia.
Yeah.
And Francesco start to learn it. So next year is going to teach. He promised me.
Yeah. Right.
So we can have an update next year. Okay. Thank you very much, Francesco. Really interesting talk.
All right.
Yeah, we are on time. So if there are last few questions, maybe. Yes, Samuel.
May I ask? Can you hear me?
Yeah.
I'm not sure. Okay. May I ask for Francesco and Giuseppe, would you recommend that we try to process all of our data using GDAL, and then, or I mean, like what part should be done in Python, and what part would you recommend should be like we're trying to figure out like how if try to learn this step or learn the step that we taught before, and like, or maybe some part can be done in Python that's much more efficient before doing the machine learning phase. Like in terms of the data set preparation, what is the most efficient and most recommended strategies?
I think so. I did not see how. I suspect that the machine learning part, I have not have an eye on about that, but it is written. It uses pandas, and the final way to do that. So the part after you use pandas, you can go to vectorize the pandas use in order to be more efficient. But essentially, this needs to be done after the data input. So the true problem is to produce to have an initial representation of the data, which would be more synthetic and can be loaded fastly than the text file, the big text file currently in the representation. So basically, one should need a raster representation if possible. But those data are sparse, and being sparse, you cannot use a matrix. This is the essential problem. So probably it requires some form of interpolation in order to have the same data on a grid, and not regular on a sparse grid, but in a regular grid. But that should be checked to avoid to interpolate if it is required to interpolate some data and so on, in order to apply the machine learning part in the successive part. But often the problem is that you have to cope with the input data that are not under your control. You have to work with that, and so simply try to find a more efficient way to use those data. So, for instance, by the sampling, just like in this case, and try to use a way to find a way more efficient to manage those data.
Yeah,
to give you an answer, an answer about that.
Yeah, let me adding also, so far we have been seeing the use of Bash for geographical operation together with GDAL and PK tools. Okay, now we are entering a new environment with Python, and we will see. So we see raster.io, and we will see PyGeo with Peter in 2 weeks, and that one is much faster than what we see now in raster.io. So I would say I would not go for one excluding the other. I mean, between Bash and Python, but I would keep it both of them in the learning phase, carry on both of them for a simple reason, because, for example, the GDAL location info is the fast way that you can do the point extraction. Okay, so far with whatever we tested. But then when you want to do matrix manipulation or array manipulation with NumPy and so on, then you need the friendly environment of Python with the NumPy. And then, if there is a specific filter, we saw PK filter that can do square window, but you want to do oval windows and not square, something like this, you can't use PK tools, so you need to do a NumPy and build up oval windows, something very specific. Okay. So that's why we teach both of them, because then you have to balance. You have to balance which one to choose. Of course, if you are already in Python, you need to do a pattern in a matrix. You don't exit and do it in Bash and then entering again, So this is where, and we will see the machine learning operation is everything in Python. Okay, so this is a kind of transition, and the table that Francesco is built is nothing else. The table with height and all the predictor is the table that Antonio is going to use it for the machine learning regression. So we are showing, the full path between manipulate each single raster, align all of them, blah, 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 no data, whatever we explain, create a table, do the modeling, eventually to the validation procedure and so on, and then go back to the final plotting, the final prediction on the raster. So this is where we try to build a case.
Thank you. Yeah, thank you.
And of course, we are working with the full data set, which could be not required when you works to develop things because not necessarily you need to process all million and so on all the records. You could work in a subset. After that, probably in a successive phase, you need to sit and understand how you can work better with multi-process and possibly also multi-host in the case it is required.
Okay.
Thanks.
Cool. Thanks very much.
Is there is any question, Alex, or maybe the folks without the video? That sometimes they should turn on the video to say we are alive. Okay, perfect. So next week, remember, it's going to... Oops, some question?
No, I'm alive.
Yeah,
Ah,
good.
okay.
You are alive. Good. So next question, next week is going to be called, we call it catch-up session. So we are not going to teach any new concept, but please come with question and come with stuff that you have tried and doesn't work, and you want some help, let's say this way, you know, clarification from past lecture and so on. So I will be there. Maybe Francesco can join for a while, maybe. So these are really important for this kind of interaction. So try to use the data and the tools, because this is where you learn. Okay, thanks again, Francesco. And we are going to see Francesco again, maybe from time to time, and for sure he's going to be one of the teacher in supervisor in Matera.
Yeah.
Okay. Ciao. Thank you very much, Francesco, and see you for everybody.
Thank you. See you. Bye bye.
Thank you so much. Thank you.
Bye all.
Bye.
Thank you.